free body diagram, draw a free body diagram, and then derive Euler equation, for each inertia components, and then you summarize all the equation, and then put that into state space representation. But there was a lot of hands-on manual work human had to go through. So if you had to, if you want to do any kind of architecture study, configuration study, and considering multiple architectures, then you have to do this many, many times, right? Which is just not efficient, not possible. And the automated modeling comes in to automate this modeling process, okay? Then if that's possible, then it'll be a very powerful tool for research perspective. So that's what we are going to cover today. So I talked about conventional approach, and let me introduce you to automated approach. Conventional modeling. So we have like a stick diagram, cross-sectional view, and then we put that into lever analogy to be able to see what is connected to what, and then using that diagram, lever diagram, we derive governing equations and put that into state space representation. If there is two modes, if there's a clutch, then you have to do this twice, low speed mode, high speed mode. But like I said, this is very inefficient, and human, having human, driving this model for every architecture. If you want to do architecture study or design study, this is just not, feasible. So what people started to investigate, was, are there any pattern in the model? Can we somehow automate this modeling process? So people looked at that, and if you look at this state space model, the first part was, this part was J, inertial matrix, and then we have, so we have D matrix, and then we have D matrix transpose, right? This part, and then zeros, right? And then we have state vector, and then F, right? So this is all, vector, right? And then we have, torque vector, right? But of course, there's some other terms, which is road load. So this, we were able to see these patterns, right? So maybe we can automate this, modeling process. But how, right? Well, if you look at the details of the pattern, so if you look at this, let's start with easy one, okay? Let's start with omega and J, okay? And then T. So once you have, let's say, once you set up the state vector, so you lay out each state or shaft rotational speed. So omega E, omega out, mg1, mg2 for compound split, okay, for 4 states, right? And then there's internal force for PG1 and PG2. And then there's torque vector, right? And if you look at this state vector, and if you look at this torque vector, input vector, there is a clear relationship between these two. So you need to put engine torque for the engine speed, and motor mg1 for mg1 speed, mg2 for mg2 speed. And the road load coupled with output speed, right? How about J and D, right? So this is relatively easy, clear, right? How about J and D? D is more tricky. So D changes as a function of these connections, okay? So how PG is connected, right? And then there's J matrix, which is relatively easy to identify because this is coupled with, so engine inertia is coupled with engine speed, right? And vehicle mass is coupled with output speed, mg1, mg2, right? So this is easy to match. So once you fix J matrix, you can identify omega and torque, or vice versa. You can start from omega, or you can start from torque, and then you can identify other two vector and matrix, okay? So now we are left with D matrix. How do we find D matrix, right? That's the tricky part, okay? So finding D matrix is a little more tricky. So this is how we can identify D matrix, okay? So if you observe the pattern, so let's say okay, let me go through the rule first, okay? So this is how you identify D matrix. So the number of columns of D equals to the number of PG, means that if you have one PG, then you have one column. If you have two PG, you have two columns, okay? And then the number of rows of D is equal to the number of columns of D plus 2, each representing a node of the lever diagram, okay? So what that means is, so this number of row represents the number of independent nodes. So here you have 3, here you have 4, okay? So number of columns of D plus 2. Okay. All right, so if you had 1 column, then it'll be 3, 2 column, 4, right? And for the power source components at each row, the node coefficients should be entered. So node coefficients is equal to minus SI, where I equals to the PG, which PG you're mentioning, you're referring to. So if you have 2 PG, then I could be either 1 or 2. And then so S for the sun gear, R for the ring gear, and SI plus R1 for the carrier. So what that means is if you have let's start with simple one, okay? So in this case, let's say this was ring, this was sun, then this will be ring, will be sun, then I think this is not a good example because there's no components, so it's hard to understand. So let me finish this and I'll show you an example, okay? And then fill all other entries with zeros, okay? So matrix D can be further simplified to 4 by 2 using the information of the free rolling nodes. So what that means is let's take a look at this example, okay? Let me see. This needs to be PPT. This has some animation. I couldn't play this in my tablet. So let's start with this example, okay? We have PG1, we have PG2. So you form a 4 by 2 PGs, okay? Matrix. And then the column corresponds to each PG. The row corresponds to each component. So this is now omega E, omega V. So we have this vector here. So let me erase that. Anyway, so engine is let's say engine is connected to this node, okay? Then you put negative R. This was ring gear. And you put negative R here, so where PG1 and engine is connected, and that node is R, ring gear, okay? And then next, you move on to the vehicle. So vehicle is connected to this node. But this node is also connected to this node, which is carrier. So you put R1 plus S1 for PG1 and R2 plus S2 for PG2. And then next, MG1 is connected to this node, which is sun gear. So you put negative S1 for the PG1. And then MG2 is connected to this node, which is sun gear of PG2. Okay. Now you're done. Rest will be zeros. Okay. So it's not that bad, right? So you just need to repeat this process. Okay. So if you have this lever representation, you can directly get this D matrix. Okay. Or you can also do this. Let's say you have matrix. And then you can draw lever diagram, which is not here. Here. So look at this part, okay? So this is 2 mode, okay? This is low speed mode. For high speed mode, now we have this connection, but no longer ground, okay? Now, so remember when we had 2 mode, we had to drive this twice, right? Do you remember? But now all you have to do is change this value, this R2. That's all. Because now connection is linked with MG1, right? So for MG1, you put negative R2 because MG1 is also now connected with ring gear of PG2, right? So this is all that had to be changed. That's it. Rest are equal, right? 그래서 이게 0에서 이렇게 바뀐 거죠. This is so much easier, right? 어떤 면에 좀 허무하지 않나요? 이거를 매뉴얼리 다 우리가 드라이브 할 때는 손으로 다 따로따로 다 드라이브를 했는데 사실 패턴만 잘 살펴보니까 이 베리어블만 사실 하나 바꿔주면 되는 거였던 거예요. 이 커넥션이 바뀌면서. 네, 굉장히 파워풀하게 쓰일 수 있겠죠. Right. Let's continue. So I have a few more examples. Okay. So let's do this for Toyota hybrid. Okay. So Toyota hybrid has an input split, motor 1, and the vehicle was connected to ring. Generator was connected to sun. Engine is connected to carrier. So we have 1 PG, 1 column. Engine row, you put down R1 plus S1. For vehicle and MG2, you put down minus R1. For MG1, which is generator, you put down negative S1. Okay. So easy. Do you remember how we drive Toyota hybrid system model? This is all you had to do. You know, you just put down omega here, and then you need to find J, then torque, and you're done. Just D is probably most tricky part. How about Toyota hybrid system THES2? One with speed reduction gear, which had 2 PG. So the lever representation looks like this. Then we have 2 PG. The second PG is used as a speed reduction gear. So one is grounded. So you put two row and then 4 components, and then you repeat the process. Boom, that's it. Continuous. So we also looked at another Toyota hybrid system, which was high performance rear wheel drive hybrid, which had 2 speed reduction gear. So we had to go through all of these equations, but now this is all you need, okay? So you have two mode, okay? I mean, you could say mode. Low speed speed reduction gear and high speed speed reduction gear. So this was so low speed and high speed, okay? Low speed, high speed. So this part changes, okay? And all you have to do is just derive this D matrix where, can you see the difference? Oops. So the only difference becomes this value changes, okay? Because you're using different gear ratio for the speed reduction gear, okay? But rest stays the same, okay? Anyway, so Allison hybrid, we talked about this, low speed, high speed. We just need to find D matrix for the 2 mode, and then Tim can even 3 PG. We can do 3 PG, so 3 columns, okay? And then we need 5 nodes, okay? 5 rows, okay? So this can be so powerful, right? So depending on the clutch, we can change, okay? All right, and this is summary of the examples, okay? So we looked at 6 examples, and then all we had to do was come up with these D matrix. That's it, right? There's 7th powertrain, which is one of the most complicated one. Voltac 2nd generation. So it has 5 modes, 2 clutch, and 2 PG. Okay. So there's 1 motor EV, 2 motor EV. So this is EV. This is HEV. Okay, so This is the D matrix for 2 EV modes, okay? Then these are 3 hybrids modes for the D matrix, okay? So it continues, okay? So Voltec has 5 modes, so it needs 5 sets of D matrix, okay? So you only have to change, when connection changes, you just need to change D matrix. So what does this mean? You know, we have this automated modeling tool. How can we use this? You know, this may seem very useful, right? So this is one example, okay? Previously, when you do research, you start with a given configuration, given architecture, okay, and then you draw a lever diagram, and then you drive the model, right? So it was this process. Process was this way. But we can also do this, meaning that given a model, D matrix, we can find corresponding architecture. What does this mean? You know, so here, this is just model, right? And you can, using this model, put this matrix in the model simulator and do fuel economy tests, acceleration tests, you know, all kinds of, you know, performance tests you can do, you know, static analysis, whatever you like to do. And if you find that this one model, one architecture turns out to be very good, provides very good performance, then you just need to realize this into a lever diagram, and then further to, you know 3D, you know, manufacturing design, okay? The kinematic diagram, right? The one, you know, something like this, right? So this, and we can do this, okay? Are you guys following? Interesting? So Tuma will give you guys a talk next Tuesday about this architectural study, okay? So to understand that seminar, these information plays a important role, okay? So now you understand these concepts, now you can start understanding what Tuma has to talk about, okay? So hopefully you can enjoy her talk, okay? All right. So it all started from these things, you know. And then there's optimal sizing, control of split hybrids. So there's configuration, component sizing, and optimal control, and so forth. So there are many things. And then there's, you know, gear ratio. We can optimize, you know, sun gear, ring gear, you know, PG gear ratios can change performance, which is also coupled with control, which is also related to component size, and then architecture, configuration. So there are many design variables. Architectural level, gear ratio, control, components, component size, 10 kilowatt motor or 20 kilowatt, 50 kilowatts, what is optimal, right? From fuel economy perspective, so we have also fuel economy, but we also have acceleration performance, right? So we need to tackle all of this, right? So this is a huge design space and large problem. And in the past, people have been, tackling this problem, large problem, by reducing the problem, meaning that, try to reduce the design space, based on their engineering intuition or experience. So, if you connect this with this, then, maybe we can operate this as a, hybrid powertrain. So let's remove this, or if you connect this with this, I think this is going to be a good powertrain, so let's, investigate, So in the old days, if you look at Toyota hybrid system and Voltec and GM Volt, they evolved their architecture. It took 20 to 30 years to get to current architecture. They tried different architectures, and then as they move on, they optimize their architecture, their component size, their control. 강의 중이라서요. 네, 미안합니다. 어디서 멈췄죠? Yeah, so there are so many things we have to optimize, okay? And people have been doing this based on their sort of feeling and some engineering knowledge and experience. But what we wanted to do was do this, systematically, without losing any unexplored space, because previously people dropped a lot of design space because they just couldn't investigate all the spaces. Okay, so that's what we have been working. Tuma and I have been working on this, and Tuma is going to share some of her old works with you guys. Okay. So, so as an example, so if we have powertrain 1 and powertrain 2, we're going to model, so we can use the automated modeling, and then do the, gear ratio optimization using DP for optimal control. Now we can compare powertrain 1 with powertrain 2. So if you want to compare powertrain 1 with powertrain 2, to make sure this becomes a fair comparison, what do we have to consider? I just mentioned that, right? I mentioned here. We have to consider fuel economy, acceleration performance, control, gear ratio, component size, configuration, right? So this is configuration. We are comparing two configurations. Let's say we also fixed component size. Then we are left with gear ratio and optimal control, right? So meaning that if you want to design, powertrain A with powertrain B, to make sure this becomes fair comparison, you need to investigate their fuel economy with optimized gear ratio and optimized control, right? If you compare architecture A with B with one fixed controller, then it's not fair comparison. Or also, if you fix gear ratio, then it's not a fair comparison, right? Maybe powertrain 1 is optimized, but powertrain 2 was not optimized, So to become fair comparison, you need to optimize both, right? So that makes a comparison very challenging or time consuming, right? Because you have to optimize, for days or weeks, if you're considering all the design space, right? So this is what, before, 2010, people have been this kind of comparison with limited number of powertrains. Okay, so people, say, oh, this is good architecture. Okay, that's it for today for lecture material. Next Tuesday, Tuma will, like I said, share some of the state-of-the-art architecture study with you guys. So hopefully that interests you. And then I'll give you guys my last lecture